All right, this unit is on the atmosphere. You're going to be learning about the air around you. What is it comprised of? What's its composition? How much oxygen does it have? Then you're going to be learning about air pressure and density, the 4 layers of the atmosphere and what happens within them. Then we're going to talk a little bit about sunlight and how it affects the temperature of the atmosphere. And lastly, we're going to be talking about wind and where that happens and how that happens. So have fun. All right, so this first part is all about what the composition of Earth's atmosphere is. So we're going to be able to describe the composition of the atmosphere. And in that, you may think that all oxygen or all the atmosphere is oxygen or what we breathe in every day, but actually only a small part of what you breathe in every day is oxygen. We'll talk about that in a minute. So this is a key. You need to know this. Know it, know it, know it. Then there's also a couple of vocabulary words within this section. Weather and atmosphere. You should already know those, but weather is the condition of Earth's atmosphere at a particular time and place. And then atmosphere is the envelope of gases that surrounds the planet. So it's not just what's here, it's all the atmosphere that goes all the way up, all the way around our planet. The gases in our air are actually made up of different gases. You may think that that's just oxygen for the most part because that's what we hear about that we need within our body. We say, I need more oxygen, right? However, actually, the biggest part of our air, this big part, is nitrogen, and that's about 75% of the air that we have is made up of nitrogen. Oxygen here is this other big slice here, and it's about 21%. Okay, so that leaves us about 4% left over for carbon dioxide and other gases. Now, carbon dioxide is less than 1%, right? Less than 1%. And then the other gases make up the rest of. The atmosphere is also made up of other things like we talked about, such as water vapor, which, as you know, is the water in the form of gas, and then also other particles in the air, such as dust, smoke, salt, chemicals. Sometimes you can see those, but most of them are too small. You won't ever see them. Now, you may not think that air has any sort of existence around you. You can't see it. You can't typically smell it unless it has something in it. You can't feel it. However, we know that it is there, and it consists of atoms and molecules, and those have mass. So therefore, air has mass. It also has other properties, including density and pressure. Most of you should know right by now that density is the amount of mass in a given volume. So if you're given a volume of something, you can figure out how much mass it has, and that is its density. How much weight it has is another way that sometimes it's thought of. The other item here is air pressure. Air pressure is the result of a weight of column of air pushing on an area. Take a look at the next slide to get a better idea of what that is. The air above you, actually all the way up throughout the entire atmosphere, is all pushing down and pressing on you. That's what air pressure is, right? So you've got this column of air, and amazingly, the weight of all of that is about the weight that you would find in a school bus. It would be about that heavy. However, why don't you feel that? I mean, if it's all sitting right on top of you, how is it that you don't feel it? Well, the air is actually pushing in all sorts of different directions. So though you have air pushing down, there's also air molecules that are pushing up and out and to the side. And so they're all balanced as they push towards you. There's air that is pushing up at the bottom of your desk that is pushing up on the air that is pushing down. And so it all balances out so you don't actually feel it. Okay, layers of the atmosphere. Now, in our atmosphere, there are layers of it, just as if there were layers on the inside of our Earth, like we talked about. In this case, the scientists divide the Earth's atmosphere into 4 main layers, and they're classified according to their changes in temperature. The layers are the troposphere, the stratosphere, the mesosphere, and the thermosphere. And we're going to talk about those in more detail. The first of the 4 layers is the troposphere. This is the smallest of all the layers. It is an average of about 12 kilometers thick. However, it can be as much as 16 kilometers down towards the equator and as little as 9 kilometers thick up towards either of the North or the South Pole. Now, however, even though this is the smallest of all the layers, it is actually the most dense of all the layers too. It has the most molecules of air and has the most mass in our atmosphere. It actually contains almost all of the mass of the atmosphere. Now, the temperature changes also within this as the farther you go up in the atmosphere, the farther you go up in the troposphere, it actually gets colder and colder and colder until it gets to approximately negative 60 degrees Celsius where it stops. It no longer gets any colder than that. Now, our next layer of the atmosphere is the stratosphere. No, this is not the stratosphere that hangs out down on the strip. This is the stratosphere that is within our atmosphere. Now, this goes up to about 50 kilometers above our Earth, and its lower layer down here towards this bottom edge is cold. It's about that negative 60 degrees Celsius. Now, however, the further up within the stratosphere that you get, it gets warmer, and that's because of the ozone layer. Now, if you don't know what the ozone is, ozone, O-Z-O-N-E, but the difference between this form of oxygen is that it has 3 atoms in each molecule instead of the usual 2. So when the ozone absorbs the energy from the sun, that energy is converted to heat, and it warms the air within that stratosphere layer. The ozone layer also protects the living things on Earth from those damaging ultraviolet radiation rays that come from the sun. Now, some of you may have heard, actually, that the ozone is a bad thing. Ozone within our air, actually down here on the troposphere where we live, it is a bad thing. It's a pollutant. However, when there's ozone up in the stratosphere, it's a good thing. It captures those bad rays that we don't want to come to the Earth that can actually harm us. Now, some scientists use the phrase good up high, bad nearby to describe those helpful effects of the ozone in the stratosphere and the harmful effects it can have here in the troposphere. Now, our third layer is the mesosphere, and this mesosphere extends to approximately 80 kilometers up from our Earth. And the difference between the stratosphere and the mesosphere is actually marked where the temperature changes, right about that area, to a negative 90 degrees Celsius. So it takes a big jump there. Now, this layer plays a very important role in our Earth because it actually protects us from being hit by meteoroids. Now, meteoroids, as we know, are just, stones and rocks and metal and those sorts of things that are coming from space. If you've ever looked up into the sky and you've seen a shooting star, that trail that is left behind by the shooting star is actually the meteoroid being burned up within the mesosphere. You may wonder how it could burn up if the temperature is that low 90 degrees Celsius. However, they're not actually burning up. It's actually a reaction from the friction with the gas molecules in the mesosphere that causes it to burn, as we say. And the last layer of the atmosphere is the thermosphere. Now, the thermosphere, though it looks as if it's pointing to just this spot right here, it's actually all of this, up. It begins at that 80 kilometers section, right? And it goes all the way out to the throughout our entire atmosphere. There is no stopping it. It goes on and on and on. Now, in the thermosphere, you would expect that you would see the temperatures continue to decrease, but that is not the case. This is actually where the temperatures increase. And amazingly, because of the sunlight striking the thermosphere, it can get very, very, very hot, and it can actually get up to 1800 degrees Celsius. And that is a positive, not the negative that you saw over here. It's a positive 1800 degrees Celsius. Now, within the thermosphere, there are 2 layers. The first is the ionosphere, and that actually comes up to about the 400-kilometer mark, so from about 80 on up. And that is, again, the IONO sphere. Okay, and then the other one is the exosphere, obviously EXO sphere. And that one is that 400 and up. Now, the cool thing about the ionosphere is that that is where the auroras that you can sometimes see up in the northern parts of the world, that is where they actually occur. When the sun strikes the atoms in the ionosphere near the poles, it creates those really pretty different dancing colors. This next section is about energy in Earth's atmospheres. Now, some sunlight is absorbed or reflected by the atmosphere before it can reach the surface of our Earth, and the rest passes through the atmosphere to the surface. Now, I don't want to talk about the different types of waves. We'll possibly deal with those when we hit chemistry and physics next year, but it actually has a couple of different sorts of energy rays that come through with the sunlight. So most of the energy from the sun, it travels to Earth in the form of visible light and infrared radiation. Now, a smaller amount arrives as ultraviolet radiation, which is what we talked about with the ozone layer and what it captures. Now, this last one here is the greenhouse effect, where gas holds heat in Earth's atmosphere. We'll talk about that in another slide or two. Okay, so when energy hits the Earth's surface, when the sunlight rays come down, come through those various layers of our atmosphere, then some of that sunlight or some of those rays kind of get some different things happening, right? They don't all get absorbed by our Earth. Some are reflected, some are absorbed, and some are radiated. So if we look at this picture and we use these words and we figure out what goes here. So let's look at this. So this first one here shows us that about 25% of incoming sunlight has something done to it by clouds, dust, and gases in the atmosphere. This one here is reflected. So it's reflected. It's bounced back up off of the clouds back out into the atmosphere. Now this next one here, this one right here, it states that about 20% is absorbed by gases and particles in the atmosphere. So it's just kind of taken up in those gases and those different particles, and they just kind of take that heat in. Now let's take a look at this one over here. This is a big one. About 50% is also absorbed by Earth's surface. This heats the land and the water. It heats everything. This is what you feel like when you're walking across the ground and you feel that heat coming up off of the sidewalk or off the dirt or the grass. That's being absorbed. That's where the sunlight has been absorbed by our land and or water. Now, some of this bottom one down here, some absorbed energy is radiated. You guys should remember that word back from when we talked about radiation and convection and convection. So then this last one down here, last one. So this one has about 5% is, let's say, reflected. So again, this is another reflected where it actually heads back into the atmosphere when it hits the surface of our Earth. The last section about the sunlight and the atmosphere is about the greenhouse effect. Now, the greenhouse effect is just like what you would expect it to be. What happens in a greenhouse? A greenhouse, it traps energy inside and allows plants to grow. Well, the same kind of thing is here, right? The greenhouse effect is a natural heat trapping process. This process actually holds heat in our atmosphere, and it actually is what allows our temperature to stay somewhere that is comfortable for most living things on our Earth to live in. Now, scientists have found evidence that states that we as humans on this Earth, our activities are actually altering this process of the greenhouse gases. However, we'll talk about that when hopefully we get to it at the end of the atmosphere weather climate unit. This last section, I'd like you to take a look at this picture here, and these all happen in a specific order. This one is number 1. The sun's energy reaches Earth. Then it hits Earth's surface and is heated. Now the next thing it does is some of it is radiated off into space, but some of it is radiated heat that is absorbed by gases in the atmosphere, which is causing that greenhouse effect. Now this last section is on winds. Now we know that the air is kind of like a fluid. It kind of moves from place to place. Well, but that happens because air pressure causes it to move. Winds move from areas of high pressure to areas of low pressure. So most differences in air pressure are caused by the unequal heating of the atmosphere. I'm going to talk about this on the next slide because I'd like to actually draw you a diagram of how this works. So just quickly, these are just a couple of more vocabulary words that I want you to remember. This is the anemometer, which is a 3 to 4 cup mounted on the ends of spokes that spin on an axle, and this is used to measure wind. I have one in the classroom. Ask me about it. And then the other thing is the wind chill factor. Now the wind chill factor, you've heard this on the news, although not so much here in Vegas, but this is where the wind actually causes an increased cooling, which changes our temperature, or at least what we feel of the temperature. Okay, so back to our wind currents. So again, you know what convection currents are. We've dealt with these when it came to water. We dealt with it within the liquids inside our earth. Well, these also actually happen with the air temperature above our earth as well. So if we have the surface of our earth, and I'm just going to draw that as a blue line because we're known as the blue planet, right? So this is our Earth's surface. Now, if I have heat coming down from the sun and it's heating this surface, so we're going to get some heat, right? What is going to happen to that surface? Well, the air over it, all these particles of air out here, are going to heat up. Now, what happens when it heats up? It becomes less dense. Now let's suppose that we have another surface over here, but this surface over here, it doesn't get as much heat. It only gets 1 arrow's worth of heat, right? So the air above it isn't going to get as warm. It's going to get a little warm, but not as much. Now what's going to happen to that? It's not going to get quite as less dense. In fact, it's going to become denser because it's going to be cooler. This one was warmer. So what's going to happen is we're actually going to have this air that's over here, which is cooler, is going to flow right at the bottom level. This air up here is going to be warmer. And actually, let's go ahead and change this color down here to blue so we know that this is the cooler air. So this air is going to be cooler, and this air is going to be warmer up here, and this is going to cause our convection currents to occur. It forces the warm air to rise because we've got that cool air that is going on underneath. Local winds, that's our next thing we're going to talk about. These are the ones that blow over short distances. This is a key word here, short distances, and it's caused by an unequal heating of Earth's surface within a small area. Another key word there is the small area right there. Okay, now a couple examples of these are sea breezes. Now the other thing we're going to talk about here is global winds. Global winds are ones that blow steady from a specific direction over long distances, and they cover a large area. I'm going to go into a little more detail here in just a minute on both of these. Two different forms of local winds are sea breezes. Well, that's one of them. And these actually happen when you have cold air moving in over water, and it comes over onto where we've got land over here, right? And on this land, our warm air moves up, and our cool breeze comes in and takes its place. And that's why you feel the wind when you're over by a body of water, such as the ocean or a lake. Now, the other one is land breezes. And land breezes are exactly the opposite. So if we have land and we have water, you're actually going to find the opposite happening, right? Where warm air is coming off of the water and cool air is actually moving off of the land. Back to global winds. The first thing we're going to do is we're going to look at this. Now imagine that the sun is out here and it's shining down into these regions. Now, which part of it is going to get the most intense amount of the sun's rays? That's going to be right here in the center, because this is where the rays are going to be shooting straight down from directly overhead, and it's going to be very intense in those areas. Imagine kind of like a magnifying glass if you were to focus the sun's rays on one spot. If you're looking directly down, it's going to be one tiny little direct spot. Or maybe think of this, actually even a better analogy would be if you think to like a flashlight. If you're pointing the flashlight straight down or straight at something, you're going to get a little circle. However, if you're pointing it at an angle, you're going to get a big oblong shape that happens where it's not directed. So you're going to get some fading towards one side, a little more intense at the one side. Now that is what is occurring at our poles up here. You'll notice they've got big, long, oblong shapes where the sunlight is hitting them. So it's not direct, and so therefore not as intense. Because of these sun rays hitting at these different things, you're going to find the temperatures are going to change at the poles. It's much colder at the poles than it is there at the equator. So what does this mean for our global winds? Well, it's all about convection currents. So these convection currents are occurring within our atmosphere, and especially with these global winds, right? So the temperature differences between the equator, where we have these warm air currents occurring, and the cold air currents that are occurring up here on the poles. Well, remember, these are density issues, right? So our warm air currents are going to be less dense, and our cold air currents are going to be more dense. So cold air sinks at the poles, and warm air at the equator rises. So pressure differences cause surface winds to blow from the poles toward the equator. Air flows away from the equator and toward the poles higher in the atmosphere, and these air movements produce those global winds. Now, the cool thing is that Coriolis effect. You briefly learned about this possibly back in the water unit. So let me write that word down. That is the Coriolis effect. So the Coriolis effect. So if our Earth did not rotate, right, if it was just sitting there, it didn't do anything, then these global winds would just blow in a straight line across the Earth from poles towards the equator. But because our Earth rotates, right, they don't follow a straight path. Instead, they curve. The winds curve around our Earth. Now, the interesting thing is that in the northern hemisphere, these winds will gradually turn towards the right. So that's this one here is going to turn this way, and this one here is going to turn this way. However, in the southern hemisphere, they're actually going to go the opposite direction because the wind is blowing towards the south. So these warm air currents are going to go in the opposite direction, as are our cold air currents that are going to go towards the left. Okay, this is the end of the atmosphere unit. Make sure that you have watched this twice. The first time, again, just watch. The second time, make sure that you have written down notes. Write your notes. And that is the end.